Let's continue on with some more examples using skin folds and DEXA-determined composition, and let's see about standard errors and errors of prediction. And let's illustrate that graphically with some figures.
Assume that this box represents the variance in DEXA-determined percent fat.
What measures might we use to estimate or measure DEXA percent fat? How much variance is there in DEXA measured body fatness? Well, if you have a DEXA device, you measured percent fat, there's actually very little error in measuring DEXA-determined percent fat. But it costs a great deal of money. It's not very feasible. So what measures might we take instead of DEXA to estimate percent fat? The first measure that might come to your mind is skin folds. What if we took skin fold measures to estimate DEXA-determined percent fat? Let's take 3 skin folds. If we did that, how much error is there? If the correlation between 3 skin folds and DEXA-determined percent fat is 0.9, R squared, the coefficient of determination, is 0.81. So we would have this figure to represent how much error there is in estimating percent fat DEXA-determined from skin folds. Notice, 0.90 squared is 0.81. 81% of the variation DEXA percent fat can be counted for by knowing 3 skin folds. But what if we wanted to use a different measure, or something more feasible? What if we wanted to use, for example, BMI?
So if we measured everybody's BMI and correlated that with percent fat, how much error would we have if the R was 0.6 and the coefficient of determination then is 0.36? The amount of error has now gotten quite a bit larger with a more feasible device.
Even though the correlation was moderate, 0.60. What if we chose a different measure? What if we chose to use a single skin fold measure rather than 3 skin fold measures? And what if the correlation then was found to be 0.50? R squared is 0.25. Look how much error there is now. 25% of the variation was accounted for in our example.
And 75% now is error.
So what's happened to the standard error? As we went across here, the errors have become larger. What if we wanted something even more feasible? What if the predictor that we wanted to use was hair color? What's the correlation between hair color and body composition? That correlation is
0, as you might expect. The coefficient of determination is also 0. We have all error in the measurement.
So there's no advantage in using hair color to predict or estimate percent fat.
With a correlation of 0, there is all error and thus no prediction possible.
Notice as we went across these different measures, the error increased. So now let's summarize those and see what it looks like. Here's variance in DEXA-determined body composition. It has very little error if you did DEXA. It has more error if you did 3 skin folds. It has more error if you did BMI. It has more error if you did a single skin fold. And it has the most error if you did hair color.
Another look at that would be to look at the scatter plots. If we have a perfect correlation, we have a straight line. With a high correlation, we have a little bit of error. With a moderately high correlation, we have a little more error, and you can see as you go across down to no correlation, we have all error.
So you have to make some decisions. What kinds of measures are you willing to take? What happens here? As you change the measures that you're taking, you have more error in prediction. So as the error increases, the feasibility increases. So you have to make a decision.
How much error are you willing to live with to gain feasibility?
Note what will happen. The standard error of estimate will increase as the correlation approaches 0. The standard error will decrease as the correlation approaches 1 in absolute value.